Good morning, good afternoon. The topic of today's presentation is thermodynamic efficiency of self-organization, and I will try to introduce this concept with a few case studies arguing that there is a principle of the super-efficiency following which different systems maximize this particular quantity, thermodynamic efficiency, at phase transitions, at critical regimes. So there is, in fact, a distinction between this quantity, thermodynamic efficiency, and the classical quantity of thermal efficiency. And in part, in this presentation, I'll try to explain what is the difference here. I did mention phase transitions and criticality in general, and pretty much all these examples, case studies that you see here, are going to be studied from this perspective, what happens at a critical regime. Part of the technical content will be drawing from information theory and classical thermodynamics, and one measure in particular, Fisher information, will be quite useful in finding this bridge between the thermodynamic quantity on one hand and computational quantity or interpretation on the other hand. So let me begin with the classical definition of a thermal efficiency. There is nothing mysterious here. This image is actually taken from Wikipedia. So we have some system and a process which is occurring within the system with some inflow of energy and some useful work extracted from the system. Given some loss, some thermal loss heat, for example, which escapes this system without producing any useful work. So when you talk about this heat balance, you have some benefit which you could extract and some cost that you spent, and obviously the useful work taken out in the numerator divided by the energy which has been consumed defines the thermal efficiency of this process. In a very general sense, there are many other definitions of efficiencies, but in a very general sense, you talk about the ratio between a benefit and a cost. Joules divided by joules. So the thermal efficiency is dimensionless quantity. But what if the question is slightly different? What if the question is not about the benefit measured in terms of the work extracted out of the system, but rather how much gain do we get in terms of predictability of a process which may be self-organization? In that sense, we still follow the idea of benefit divided by cost, and cost still remains to be thermal, but the numerator here will be defined in entropic terms in bits. So to unravel this picture that pretty much is an extension of that old Wikipedia image, we're talking about some interactions happening within the system, and we say that there is perhaps some self-organization going on, and that's why this question about gain and predictability is immediately applicable. So the benefit is here measured as the increase in order. Presumably, if it is a self-organizing process, we should get some sort of increase in structure or in function, or in general case, some increase in predictability in order, which we define as a change in entropy at a particular change in the underlying parameter theta. So you see it becomes dependent on a value of this parameter, and I will exemplify what this parameter could be. But in general, it is a control parameter. You have some protocol which drives the system, but looking at the increase in order, negative entropy per parameter, that becomes the numerator. What is the denominator here is not the initial input in energy terms, but actually the work which we already extracted. So you see, this measure of thermodynamic efficiency is a quantity which relates that increase in order, but how much of that work was converted into the increase in predictability. So it's a change in entropy, which measures increase in order, to the change in generalized work at the same value of this parameter. So obviously, when you talk about dimensionality, you could see immediately that the parameter unit doesn't matter, heat cancels out, and what you actually end up with is bits per joule. So now let me switch the perspective here and talk about, again, very classical notion of phase transitions and order parameters. So again, you have a control parameter on the x-axis here, and in case of magnetization or ferromagnetic or paramagnetic phase transitions, in this example, we talk essentially about the Curie point. If you reduce the temperature a little bit, isotropic, disordered orientation of these spins makes no magnetization. But suddenly, at the Curie point, magnetization does occur and material becomes magnetic because the spins become essentially coherent. Their orientations lose symmetry and become anisotropic. So that change happens abruptly, and in general, you could talk about phase transitions of different kinds, first order, second order. If it is discontinuous second order phase transition, you get a sudden onset of order, and the order parameter, in this case, some normalized magnetic moment, jumps from being 0 to being 1 in a relatively abrupt fashion. So what happens when you look at the derivative, first derivative of this order parameter, which again you could see here from one of the seminal papers on the topic, you see that the first derivative of this order parameter diverges at exactly the phase transition because the derivative here takes this quantity proximity to the critical point with some exponent, so mathematically it is divergent. Now I will bring it together with the notion of Fisher information, which in general is measure of sensitivity, the sensitivity of the probability distribution P of x to changes in theta. Going back to these orientations of spins, for example, say it was completely isotropic, symmetric, no preferred orientation, and say we measured the probability of preferred orientation. So it was completely random, isotropic, and it would be not very sensitive if this distribution changed a little bit to something like that. On the right-hand side, you actually have preferred orientation, which is anisotropic. And again, if you look at on the right-hand side and make a small change in the underlying parameter, say the temperature of this material changes a little bit, you get then you get a slight change to a different orientation. But again, how sensitive is this change to the change in theta? And that's exactly what Fisher information is trying to measure, the change to the underlying change in the parameter theta. So the change either on the left, if it was completely random, or on the right, when it was completely magnetized or oriented in a preferred direction. In either case, the change is not very large, and the Fisher information will be low in both of these cases. But if, for example, you change from left to right, from the left to the right, you will obviously change this probability distribution quite dramatically. And that change would be quite large relative to the either extreme. And that's exactly what happens at the phase transition. But what happens mathematically, we derived a very simple relationship that the Fisher information, in fact, it's a Fisher information matrix, given that you could have multiple underlying parameters, theta, and multiple order parameters, phi. In a simple case, on a diagonal, you have conjugate parameters, and the derivative of the order parameter with respect to the control parameter is exactly proportional to the Fish information. And the next derivation is essentially starting from the very same definition of Fish information, relates that same quantity, f of theta, to the second derivative of the generalized work. So not only we show that the Fish information diverges at the phase transition because the first derivative of the other parameter diverges there, we also show here, and that's more recent work 5 years ago, is that it is in fact proportional to the negative curvature of work. This formula has been derived for quasi-static processes, meaning that the change in the underlying control parameter is very slow. And now we will be using this formula in relating it to this quantity of thermodynamic efficiency, which I started with. So it was defined like that in thermodynamic terms. To remind you, it's the gain in predictability to the change in generalized work. And you could immediately see, because I just showed you a formula which mathematically related the second derivative of the generalized work to Fish information, it becomes a very simple exercise to plug that formula at the top right into this thermodynamic efficiency definition and derive the same quantity in computational terms, not in thermodynamic terms, but in computational terms. Why do I call it this definition computational? Because, well, the numerator was already entropic, and it's clear that it's related to Shannon entropy, which has been implicated in theory of computation quite well. But the denominator is quite curious because, you know, going from first derivative to the integration, given the second derivative relation, requires some bounds of integration. And these bounds happen to be between theta, the point at which we measure the thermodynamic efficiency, to the point theta star, which means the point where no work is done at any change, at the change of theta. So basically that's a point of zero work. So what that integration actually does, it accumulates Fisher information, which was the sensitivity of the process to changes in theta over a path, which you could argue is a computational path between the point of zero work to the point of interest. So the sensitivity of the process is accumulated along this path and then related, that's basically your computational cost in a sense, and that's related to the gain in predictability. And that's why this thermodynamic efficiency could be also related in computational terms to these quantities. And in pragmatic sense, you don't even need to think what was your order parameter. You could only observe what happens to the probability distribution. You measure the entropy change at any value of theta, and you measure how much sensitivity, and Fish information is a measure defined in probability distribution sense, how much sensitivity was accumulated on this computational path. We started with thermodynamic efficiency defined in these terms. So how much interactions within the system computed the self-organization in a sense, and that's why we moved it to the computational definition, basically trying to capture this benefit in terms of the cost. It's still energetic cost at the bottom. It just interpreted that as accumulated sensitivity along a computational path. And the first case study is collective motion. We use the standard model of collective or cohesive motion, the classical Boyd style mobility, where you measure alignment between the self-propelled particles, their cohesion, and some perturbations in terms of noise. So basically, when you talk about alignment, your parameter strength of these alignments when particles are aligned together is A. And when you talk about cohesion, you also make it proportional. But what's important is that the number of these neighbors to which you're trying to be aligned with and attracted or repelled, I mean, that's what cohesion is about, is another parameter. So essentially, there is a strength of alignment and number of effective neighbors that you're trying to follow. Those are your two control parameters. Two extremes are shown here. On the left, there is a random incoherent motion, and on the right, you see a coherent motion. These two extremes, you could see, have been produced with the same number of effective neighbors, but with different alignment strengths J. J is essentially a product of this V0 constant and A. So alignment strength went up a few orders of magnitude here, and out of incoherent motion, you get coherent motion. And here you should see that in dynamics, in motion, where the parameter J, the alignment changes from the left to right, and or you could change the number of effective neighbors. And again, if you have too few neighbors to which you pay attention to, you get incoherent motion. If you have quite a lot of neighbors, you get coherent motion. So these two parameters could be considered as control parameters driving the system from incoherent phase to coherent phase. And that's what kinetic phase transition separates in space of each of these two parameters. So if you look at it from the point of view of probability distribution in terms of the preferred orientation, that's what you see. On the left-hand side, it was completely incoherent. There was no preferred direction right here, and it's flat. Probability distribution shows no preferred orientation. As you go through the kinetic phase transition, it starts to shape up because they all move in the same direction, and that same direction is captured by this probability. And when you look at these two quantities, numerator and denominator, you see that that's what you see on the right-hand side. The thermodynamic efficiency jumps very clearly at the point of kinetic phase transition, which is obviously known from the canonical model studies where it is. It's interesting to see that the actual entropy, the numerator, goes negative here. So that's why the gain in predictability turns it into a positive quantity. And the denominator also has its own sharp decline. So relating on the left-hand side, this blue curve to, say, the crosses here, the green curve, gives you something pretty much near zero. So the sweet spot comes pretty much at the phase transition. That's where the benefit of self-organization, creation of the swarm, creation of the flock, is maximal relative to the cost, to the work that needs to be spent to keep it together. Because at that point, it's not as difficult to keep it together as if it was a solid body. So that's the intuitive idea, and the thermodynamic efficiency of swarming behavior in a finite system obviously maximizes. So here we're talking about urban dynamics, where we have as our variables essentially financial or investment activity. The intuitive idea is very simple. If you have some flow, say income, in this case we're talking about wealth or income, from points I to points J, so it's a matrix. What you want to do, you want to find a distribution in the absence of any other bits and pieces of information. You want to basically maximize the entropy of this distribution, subject to some constraints. Like one constraint could be that the cost of commuting between points I and J, Cij, is limited by the total budget. Another constraint could be defined in terms of some sort of satisfiability or attractiveness of these different points, suburbs. And obviously there is a marginalization constraint of a kind as usual, because the earning power of everybody working rather in suburb I and taking money out of it to all other suburbs is limited by whatever financial constraint which is applied. But on the left-hand side, you see essentially classical max end given 3 constraints. On the right-hand side, you see the Lotka-Valterra component. In this case, we defined it as essentially some sort of investment activity where services are being added to the subgroup J if there is some free income to spend in that subgroup J. And that free income is defined as initial income, which you could take from, say, some census data or some financial data sets, minus the money spent on living, like rent times population. So Y minus RP gives you the free money, minus whatever services are already converted to dollars are in there. So if the free flowing money, so to say, exceed what services add, then the services will be added. Otherwise, they will be reduced. The subgroups essentially compete with each other, like in the classical predator-prey model. So services sort of move from one location to another location, depending on how people are resettling. And people are resettling essentially following the max-end distribution. So the actual model works iteratively, starting from some equilibrium and moving to another equilibrium, giving some sort of financial income flows. Not surprisingly, it's a classical max-end solution, which has 2 parameters, 2 control parameters. Alpha relates to the constraint on attractiveness, which is social disposition. How much are you attracted to other people living in the same place, or in general, you try to settle near people, but not too densely. And impedance to travel is essentially how sensitive are you to changes in costs. So alpha and gamma are the 2 exponents of a classical Boltzmann-Gibbs distribution here, and Zi is classical partition function. So that's the model. You calibrate it or you initialize it with some data from a particular city. We use Greater Sydney or Greater Melbourne. And your order parameter, that was a number of large or affluent suburbs. So you see that there is a phase transition in space of alpha. You change alpha a little bit, and the number of large suburbs concentrate in a polycentric sense quite dramatically, but we didn't notice any phase transition in space of beta. Basically meaning that in Greater Sydney, which we use here as a case study, people are not as sensitive to changes in transportation costs. So alpha, which is an interesting parameter here, as I showed, and you see that when alpha is low, people are not really socially predisposed to collective life. You get very low efficiency. As you increase alpha, you get a change, you get a transition. By the way, the red line here, vertical red line, is the calibrated data to Greater of Sydney, 0.43. And the blue line is essentially the transition. Obviously, it doesn't drop as dramatically here as on the left-hand side, but that's the nature of this phase transition. And you could see that at higher values of alpha, you get comparable values of thermodynamic efficiency. So now I will show you what it means in terms of spatial distribution. Starting with the low alpha, low social disposition, you get something like that. What you see is the population. It's essentially a monocentric, sprawling kind of phase, starting from the CBD, from city of Sydney, and sort of expanding to the urban sprawl. That's what it's called. And alpha 0.09 is somewhere here, pretty much on the left-hand side. Having looked at the low efficiency, let us have a look at the other extreme, medium to high efficiency, which is higher, the maximum alpha that we considered. You see immediately that the configuration changes quite dramatically, and you get classical polycentric urban layout with the CBD and even some other suburbs forming a clear center, while what was sprawling before forms very clearly defined other centers, like in Gosford, Penrith, Camperdown, and Katoomba in Blue Mountains. So this is the other extreme with the highest social disposition and medium to high thermodynamic efficiency. In 2016, when we looked at this Greater Sydney data, the red vertical line shows you a middle case. Its alpha is in the middle, and it's medium efficiency. And curiously, if you look at the blue line here, blue vertical line, which shows you slightly different alpha, it shows you the highest possible efficiency attainable in this setup, which is something in between. It's looking more as a polycentric, but with a little bit of a sprawl. And it's a critical regime. Epidemic dynamics. What you see on the left-hand side is a classical SIS dynamics, susceptible, infected, susceptible. The ratio of two parameters here, beta over gamma, is nothing but reproduction ratio. It's a number of agents that patient 0 could infect in otherwise susceptible population. So say for Ebola, it's on average 2. For original SARS, it was on average 4. The reproduction ratio is known to have a critical epidemic threshold, classical epidemic transition. If it's higher than 1, you have an epidemic. If it's less than 1, you don't have an epidemic. If you model it on networks, you don't talk about the classical beta and gamma in terms of infectiousness rate and recovery rate. You talk about a rate of infection nu along a particular edge on the graph happening at a particular step of the simulation, and similarly equivalent of recovery is delta. To trace infectivity of different pathogens, of different viruses, you could change the nu as if you were changing infectiousness transmissibility rate beta, essentially changing R0. On the horizontal axis, nu is changing from relatively low values to relatively high values. At some point, this particular nu, given delta we use, that would be an epidemic threshold, a phase transition. Given a very small network we considered in this particular case study, we could compute using statistical mechanics exactly the change in entropy here and a change in generalized verb. So these two quantities could be related to each other, computing thermodynamic efficiency, which will peak at that point. It's not exactly at a phase transition, which is theoretical, but given that you have only a handful of nodes in a network, it's not surprising. And with larger networks, it will be getting closer and closer to the phase transition. That brings us to the question of whether we could derive these quantities analytically in a canonical model. And this canonical model is given by Curie-Weiss model of, or Ising model, where paramagnetic phase and ferromagnetic phase are well defined, and these quantities are also well defined, our numerator and our denominator. So our thermodynamic efficiency in this model computes as follows, where you see that on the left-hand side of the phase transition in ferromagnetic case, it is inverse proportional to T, where T is the essentially normalized temperature, basically distance to criticality. And on the right-hand side is proportional to the inverse T. So as T goes to 0, as you get your parameter approaching critical temperature, critical parameter, this quantity will be diverging to infinity. And that's what this study has demonstrated. So to wrap it up, I showed you 4 different case studies: self-propelled motion, urban dynamics, epidemic dynamics, and Curie-Weiss Ising model. And everywhere we saw that this thermodynamic efficiency is either maximal in a finite system or diverging at criticality in a canonical model. I also related here thermodynamic and computational perspective and argued that there is some guiding principle. So efficiency of self-organization is maximal at critical points in dynamical systems. And that's why I would argue systems often self-organize to these points. So that pretty much is the end of this presentation. And here there are some references. Thank you.